Hello guys and welcome back. So now we're going to look at creating a constraint system. But before we do that, I want to set up an active object to use to hit this wall. So I'm going to create a sphere and let's move it this way and let's template this. Okay, and let's call this out sphere. And it's not a packed primitive, so we're going to use a different node, which is the RBD object. And this is when you need to use anything that is not a packed primitives. And this works perfectly when you don't have a lot of, when you have only one piece coming in, one geometry. So let's connect the out sphere, and I'm going to give it a initial force of 100 along the z-axis. I think it needs to be negative, so let's hit play. Yep. So let's say -20, and let's hit play. Cool. So it's interacting. Both of these guys are active. And we want to create the constraint network to hold this wall together. So the way we're going to do that is using a connect adjacent pieces. And this node figures out how the nodes are connected together, how the pieces are connected together, and then generate the constraint network. The constraint network can be generated between points. It can be generated between the centroids, and there's another adjacent points. I don't remember adjacent pieces. I don't remember what this mode is for. Yeah, so we're going to use the adjacent pieces from surface points. And what it does is it connects the centroid of each primitive of each object with its neighboring. And we can, let's lower this, let's take a look at the graph, and we can lower the search distance so it doesn't have to travel too far, and we can set the maximum connection to 2, so each piece is allowed to get connected twice. And this is how the constraint network looks like. Okay, now one very important aspect of this, if we middle click, it says a name, there's a name attribute, and this name is, you know what, let me lower this to 3 pieces. Okay, and let's set this to 1. Okay, so the way it works is it figures out how the pieces are connected together and store that information as a name attribute. So for example, if it creates a line here between these two guys, it will set a name attribute on this point. It will set the name attribute that belongs to this piece here, and then the other point will have the name of the other piece that needs to be linked. And that's how Houdini can track the connectivity of the pieces. Let's put this back to 100. Okay, and let's restore all these values. And if we look here, we created this node by default creates a name attribute. If we go under the attributes, it says pieces. We can change that. We can change it to wall, for example. But then we're using this input with the connect adjacent pieces, and then here it's overriding the name again. So we need to uncheck this because we have the name attribute. Okay, it's coming from this node, and that's what we're using to generate the connectivity. Cool. So the next information that this needs is a 2-string attribute, one called constraint name and one called constraint type. And these are the definition, or we're gonna give them a unique name that we can track them in DOPS. So the constraint name, this could be anything. I can call it my glue constraint. And for the type, you have either position, rotation, or all. And we want the all because we want to constrain the rotation and the position. Okay, these two guys. What's wrong? Should be fine. Okay, and it's going to copy this and call this CST. Now the types, the constraint types that we're going to use is called glue constraint, and this is a solid constraint that holds the pieces together. There's other types of constraints, and like the spring constraint, the pin constraint, the hinge constraint, and we're going to be primarily focusing on the glue and pin constraint. The other spring, the hinge, and stuff like that are for very small parts of the destruction. Let's say you have a wall, you have a door, for example, and you want to break the rotation of the wall. You can use a hinge. You have, for example, something hanging that needs a springy motion or is attached to a moving something moving. You can add a spring constraint. But for now, we're going to for this workshop, we're going to focus on the glue and pin constraint, which are basically the 99% of the destruction workflow. Okay, cool. So let's set this constraint system. I'm going to create a constraint network node, and this comes in after the graph, after the solver and everything. We connect this node, okay, and this node is for bringing in all constraints. If you have, let's say, 10 different constraint networks, you can merge them all together and import them with one node. And what's going to happen is this node is going to import that data one time. If you look at the this expression here, it only activates the import process one time. And the reason for that is because we don't want to actively importing the data from SOPs, because that's a heavy process. We want to import everything once and then deal with it in DOPS. The next thing we want is we want to attach the constraints that we want. Now the name that we declared here, let's call this my constraint. I don't care. The name that we created here doesn't have anything to do with a constraint type. We can create any constraint we want. And if we go under the constraints, these are all the constraints available in Houdini. No, there's more. Where do they live? Yeah, so they are under the constraint tools. The hard constraint relationship and the glue constraint relationship. This is the pin constraint, and this is the glue constraint that we're going to use. So let's create this node, and the way it works is we connect it here, and you can see it has a strength. So it basically how strong this force is, and this is the name that needs to match the name that we created in SOPs. Okay, this is how we link the data. Now we created this graph, and we want to tell it in DOPS that this is a glue constraint. So I'm going to paste this name here, and we should see the graph. Let's check. Why is this? Oh, sorry. So the next thing we need is we need to tell it where to find the constraints, which is under the out constraints, and that we should see the constraint. Why is it not doing it? Okay. Sorry. This attribute is not a primitive, is not a point attribute, it's a primitive attribute. So these two guys are a primitive attribute. And this should work now. You can see the constraint is showing up. I'm going to hide the RBD object, and this is the constraint network being displayed. Now if I disable this node, you can see the constraint is turned off, because this is what's being attached. This is how Houdini is going to deal with these or treat these constraints. They are a glue constraint relationship, and this is their strength. So let's hit play, and you can see when a constraint breaks, it will disappear. So if we hit play, you see there is a force that we have already. So let's turn this off. And the gravity is breaking these guys because there is a weight on top of them, and the constraint right now is very, very weak. So if we let it just do its thing, you see it's breaking these guys, and then as the object hits, it breaks even more parts. Now as this go, it will continue breaking. And look at the details that we have now. We have a lot of cool geometry being revealed here, and this is something you wouldn't get if this was just a flat surface, obviously, or a box. Okay, so the next thing I want to do is I want to pin this. I want to pin this area here, because if let's increase the constraint network strength. You see, it moved the entire object. It just made a hole, and then it moved everything else. I don't want that. I want the bottom part to stay still, and then based on the force, something will happen to it. So we're going to turn off these some parts that we're gonna make them inactive. Okay, so first of all, I'm gonna create a wrangle node. I'm going to create an integer attribute called active. I'm going to set it to 1. Okay, this is a point attribute. Actually, let's set it to 0, and let's go here. Let's hit play, and you can see the entire wall is not active anymore, and that's because we created this attribute. This is something that DOPS recognizes. So what I'm going to do is I'm going to set active to everything equal to 1, and then I'm going to group certain pieces. Let's see, by region. Something like that. And then I'm going to set the active attribute on those points, because this is only points now. Okay, we're going to work with it as points. I'm going to set the active attribute to equal 0 for the pieces that are selected in this group. Let's go back, let's hit play. Cool. So the entire wall is static now. Not the entire wall, sorry. The bottom part is pinned, and then everything else is active. And let's lower the constraint force. You can see the more damage is going to happen for this. Now, this is probably I'm going to show you something that I didn't plan for. We know the impact location. We know where the sphere is going to come in. Okay, we know that that's the location. What I'm going to do is I'm going to create a sphere, or actually let's just take this sphere and transform it so it's on top of this. Okay, and I'm going to create an object merge, and I need this in the graph. Okay, so let's go back, and we have our points here. Or here. Okay, this is where we're doing the fracturing, and I want to add localized points in there. I don't want to add I don't want to fracture everything uniformly. I want to only add details where the impact is going to happen. So let's convert this to a volume. Okay. And let's scatter some points. I'm gonna set this to 100. And let's add a jitter them a bit so they're not cool. And then I'm gonna copy this. I'm gonna lower the number of points to 20. I'm gonna jitter them more. I'm gonna do this one more time. I'm gonna increase this to 80. And I'm going to lower the jitter, and I'm also going to transform the points or the object. So I wanted to transform it local, so I'm going to use the $CX, $CY, $CZ, and that will place the centroid in there. Actually, let's do it here. Yeah, I scaled these points in. I'm going to increase them a bit more, and I don't need this. I'm going to turn off the relaxation. I think this is too much. Let's do 80. And let's merge all of this. And now we have more points at the center, and then as it gets bigger, we have less and less points. So let's merge this with the original points, and then let's fracture this geometry. And see, now we have localized fracture. Let's go back in. Hit play, and now we have more details, and the object got stuck, which is cool. Okay, let's lower this, and let's increase the propagation rate. This is if one constraint breaks, it the impact propagates to the other constraints, and it will hopefully trigger some more fracturing. Cool. So this is a fully functional setup now with a constraint network, as you can see, with pinned base, and this is exactly what you would use to create an entire house destruction. This is still obviously a basic setup, but it has all the features needed. Now, how do we import this back? Now, everything here is still in DOPS, and we want to import that. Now, what we need, because this is a packed primitive, we need to just import the points of where these pieces are. Okay, and what I'm going to do is I'm going to use a DOP import. I'm going to drag this in here, and what I want to do is import this RBD packed object. Okay, so the object mask is that, and I'm going to change this to fetch create points to represents object, and this is going to import a point cloud that shows where the pieces are. This obviously has pardon me. This obviously has a lot more information to tell the pieces how they rotate and the velocity and stuff like that. And what we're going to do is we're going to take this, let's copy this object merge. We're going to take this static wall, see there's no animation. We're going to take these points and deform this guy with these points. And the way to do that is using transform pieces, and this is a node build for destruction. The first input is the geometry, the second input is the points. If we play through, see we have now destruction happening in subs, and this is our final geometry. Obviously it's packed primitives, so we have to unpack it if we need to do anything to it. But the great thing about this is we're not writing the mesh and animated static mesh. We just write these light points, and they are super light. So the mesh could be even 5 billion points, and we only have to store this small amount of data, and then transform this when we get to rendering, so we don't have to cache it or anything. Cool. Thank you guys for watching, and see you in a bit.